Hi everyone, welcome to the tutorial video for chapter 33 of Winston textbook, using Solver for capital budgeting. In this chapter, we will learn how to deal with some budgeting questions by using Solver. Companies will always pursue the maximum profit, but the resource they have could be limited. Therefore, they have to allocate their resources into different projects, and the Excel solver can help with it. Depends on the goal you are seeking, Solver could answer about maximizing profit or minimizing cost. Now let's check about it. First, we look at the Excel file of chapter 33, which name is Cap Budget Temp. The file has been uploaded by Professor Rose to the Blackboard, so you can download it and use it along with the video. For my file, I've done some slight adjustments for better understanding and the convenience of my demonstration, so it could be a little different from the file you download, but don't worry because I didn't change any digit in it. Now let's back to the file itself. On the screen, you can see the worksheet of the example on Winston textbook, and I've already summarized the question for you here. The company needs to know how to allocate their resources to all these 20 projects in order to get the max NPV. Each project will be either do it or not. You can't put half of the resource into a project and receive a half benefit. Each project will last for 3 years, and the cost of money and labor are listed. The budget for money and the labor for each year are also given. Like this, the project cost and the needed of labor and the budget available. Okay, so I suppose you guys have already watched the tutorial video of Solver, so I'm gonna straightly open it and remind you that as always facing a problem with Solver model, you should begin by identifying the target cell here, set objective, and the changing cell, this one, by changing variable cells, and the constraint. But before starting using the solver, we will have to do some more little effort to the data. As you can see, the goal of the company is to acquire the max NPV, the next present value. I suppose you do know the term, so I won't explain it about the NPV. Okay. For this purpose, they have to activate their projects for manufacturing or whatsoever. Anyway, this project and which they could make profit for the company. Yes. But however, the company don't have enough resources to put in all these projects so far. So for each of them, the company will have to consider whether do it or not, like here. So now we know that the target cell is the total NPV, and the changing cell is the column here, which I already named it by do it. Then how can we calculate the total NPV? Here we use the sum product function. As we know, the total NPV is the sum of each selected project. The sum product should be do it, the blue one, times NPV, as you can see. And then for the changing cell, do it, we know that it should be binary, either 0 or 1. Because as we mentioned in the very beginning, you can't put half of the resource into a project and receive a half benefit. And also, you are not allowed to do the same project in the same time. So eventually, the value of do it should be binary, and this should be considered as a constraint. For the rest constraints, they are about the limited resources. So let's check out here. As you can see here, we listed the budget available for each year in each kind of resource, money, and the labor. So of course, the total budget we are going to use should be less or equal to the budget available. Here, this one budget used should be less or equal to the budget available. Here we are also using the sum product function to calculate the budget used. You can see here the do it times the cost year 1 and the same logic for the rest. See that? Okay, now we got everything we need, and let's go to the solver. So here we open the solver dialog, and we need to set our objective, which is total NPV. Here, this one. Okay, and we want it to be maximum. And then the changing cell should be do it. This one. Okay. Okay, then we set the constraint. We press add. The first one, as we mentioned, the do it should always be either 0 or 1. So we select the cells we want, do it. And it should be binary. This one, bin, referring to binary. And we press OK. Now we got the constraint, do it equal binary. Okay. And the next constraint, we have to ensure that our budget used will be less or equal to our budget available. So we are doing this. The cell reference should be less or equal to, this is right, constraint here, budget available. Oh, sorry. Yes, this will be right. Okay, and we press OK. You can see now we got all the constraints we want. And then we have to select a solving method. For this problem, this method is a linear problem because the target cell is computed as the sum of terms that have the form changing cell, this one, do it, and it times the constant NPV. And because also the resource usage constraint here, the budget used, is also computed by comparing the sum of changing cells, do it, and times constant to a constant. Therefore, it is a linear problem and it is a linear model. So we can select the simplex LP. This LP refers to linear problem. Okay, so we select this engine and we press solve. And here we are, we get the result. We choose to keep solver solution, and also you can let Excel generate a report for you. Press this, and you'll get the answer report. Here, ignore this one. This one were dead when I tried, so you can just see this one, answer report 2. Okay. However, if you are very focused and I suppose if you already read the textbook, you'll find that my result is different from the result of textbook. And I'll show you the result on the textbook. Here we got 9,269, but on the result book of textbook, it's 9,293. And why would it be like that? In fact, the solver has already told us answers, so let's do it again. Using with all the same parameters and press solve. There, you can see it's written here. It says it is possible that better integer solution exists. To make sure solver finds the very best solution, set the integer tolerance in the options dialog to 0%. So this time we do this again with all the same parameters, but this time we press option and see there is the integer optimality, and we should set it to a 0%. Press OK and press solve. Okay, so see, this time we got the same result with the textbook 9,293, and also the description is also changed. You can see it says when the GRG engine is used, solver has found at least a local optimal solution. When simplex LP is used, which is the method we are currently using, this means solver has found a global optimal solution. Okay, so for this situation, the textbook provides an explanation. Linear solver models in which some or all the changing cell, for this example is do it, For these changing cells are required to be binary or an integer are usually harder to solve than the linear models in which all the changing cells are allowed to be fraction. Which means if you set your changing cells like this, the example we are using, the Dewey, we set it into the binary, right? We're using the constraint. So this will make the whole problem harder to be solved if we didn't use the limitation of binary. We can let it be the fraction, and there will be like 0.5 or 0.8 something, some kind of thing will appear, and the problem will be easier. How will it be easier? There's a description on the textbook. It says, often you'll be faced with a choice between finding an answer within 10% of optimal in 10 minutes or finding an optimal solution in 2 weeks of computer time. So it's clear now. For the problem we are facing now, like this, it's too small that we can ignore the time issue. But for a bigger problem, it could take weeks to find a true optimal solution. So this is the point of the integer optimality setting. If we let the tolerance be not so strict, we can have not the true optimal result, but the calculation time will be much lesser. Okay. So this is a little thing you should notice. And also here are some more extra constraints which were mentioned by the textbook, mainly about the relationship between projects. For example, if you select project 3, you must also select project 4, or you can only choose 5 projects out of 10 from the project number 1 to 10, such as these. All these constraints can be handled in the same way we use the solver. You just add these constraints into list subject to the constraint and press solve. It is done. So I won't go further on it. If you are interested, you can try it yourself. And then we go to the next problem on the book. Here, this is the question 6, which is supposed to be another file, and it's also uploaded by professor onto the Blackboard, but I combine it for the easier to demonstrate. So I choose question 6 for another example, and it is really easy, as you can see, but it has the totally opposite concept with the former one. So let's check it out. Here is the question. Use solver to determine the minimum number of coins needed to make change for 92 cents. Sorry. So its goal is seeking minimization instead of maximization. And we can see the target cell should be the number of coins here. And the number of coin is sum of these, surely. And there's a constraint about the value of coins, which should be equal to 92 here. As you can see, some product function again, and its calculation is from the values times the numbers of coins. And here, the numbers of coins is our changing cell. And don't forget, there is still another constraint, is that you cannot cut one coin in half. If you do so, the coin will lose all its value. And this is the idea that's similar to the binary. However, there's no limitation for you can only use each coin one time. You can use them more than one time. So this time we set the constraint as integer, but not binary. Okay, so let's open the solver, set the objective. The objective is number of coins, the sum of number of coins. And we want it to be minimized. And the changing cell is here, number of coins. And we add constraints. The first one should be this value of coins should be exactly equal to 92. And the other one is the number of coins should be integer. And here we got all the constraints we need. And also it's a simplex LP. So we can press solve. And now we get the result. Okay, quite simple, right? And here is the end of the video. For the rest questions on the textbook, you can try them by yourself. Thanks for watching, and I hope you get some well understand about using solver dealing the budget problem. Thank you. Bye bye.